Good to know.
Our speaker today is Professor Hadasz from Liouville University, and the title of the talk, Equivalencies of two-dimensional CFT models and relations between theories of different space-time dimensions.
Thank you. Thank you for having me here. I'm really glad that so many people in the audience. I'd like to start with kind of personal remark. Professor Lewandowski was elected by this Rada Doskonałości Naukowej, Council of Scientific Excellence, to be a referee of my professorship application. And that's why I had the privilege to speak here. But then, let me tell you, all the suffering which is ahead of you will be due to Rada Doskonałości Naukowej. Okay? And if you whistle too loudly, I may personally reconsider writing this report. So, I mean, don't be too harsh at me. Okay? Thanks a lot. And the second remark to start with, you may have heard it, but in Krakow in the old days, there was a person called Kacper Zalewski. And he had a very strict opinion about who's a good or bad lecturer. As for a bad one, everybody knows who is a bad lecturer. A good one is the one who speaks clearly, who has important idea to pass to the audience, and is interesting. And the very good one is the one which finishes at time. So I have my watch here to set for 15 minutes, and I will not be over 15 minutes. Thanks a lot. So, okay, I'm going to speak about something which is related to my research, and the result I'm going to present towards the end of this talk are quite recent results. And there will be two somehow big questions, big problems I was interested in. The first one is the structure of moduli space of two-dimensional conformal field theories. Moduli space means possible parameters which are in the theories, different type of theories, how to understand some relations in this moduli space of conformal field theories. And the second subject is related to the well-known for some time AGT relation, where some objects in four-dimensional space-time, like partition functions, especially instanton contributions to partition functions, are related to objects in two dimensions. Okay, there is still a progress. This subject about AGT is about 10 years old, maybe slightly more, but I think there is still some progress. And these are the type of question I will discuss. And since it's not a modesty, I'm a person of a bit limited intellectual abilities. The only thing I can really understand are those I can touch. And in mathematics, I mean things that I can actually calculate. And since I know that you are from, at least some of you, from the relativity group, you may not be familiar with notions I will use. So I will try to be as explicit as I can, and I will try to hide any calculational details, not showing them. On the other hand, since this will be a talk on mathematics mainly, I will try to give you some ideas, maybe even some notions as a part of a language. So if you stumble upon them sometime, you may know something about them. Okay, so let me start with something which is very simple. Namely, suppose I have a field on a complex plane, not even a field. I have a complex plane, or two-dimensional real plane with complex coordinates, and I have two vectors in such a plane. And then I can write down the Euclidean scalar product by writing the product of their z and z bar coordinates in such a way. This is, Hermitian. This is real product because u and v are real vectors, just the complex coordinates are introduced in such a way. But then you may easily notice that if you change in a holomorphic way coordinates on this plane from the coordinates Z, I'm going to coordinate W, and they are related by some holomorphic function. Then this is the way how the components of the vectors transform, and it's immediate to see that such a transformation does not depend the ratio of the scalar product over the root of a norm, and this is just the angle, right? So this is the way one can see that holomorphic transformation does not change angles between intersecting curves. So this is a holomorphic transformation, right? And then, once I have this, I can ask, suppose I have a scalar field, scalar under this transformation. Something very natural, transformed field in a transformed point is equal to untransformed field in an untransformed point. So I can write a transformed field in an old point as an old field in a point shifted back. And you clearly see that this is given by to the first order on my infinitesimal parameter. This is given by action of a differential operator of the first order, right? Because I just Taylor expanded and keep the first term. And having this operator's first order, it's immediate to check that they satisfy this simple algebra. Okay? This is a classical transformation. On the quantum level, I have my Hilbert space. I have some, say, for the scalar field, this will be some set of simple modes. And I want in this quantum theory to construct representations of those operators in my Hilbert space. But since in the field theories, this Hilbert space is infinite dimensional, I have always kind of normal ordering issues. And due to these issues, rather than having the algebra as before, there in all non-trivial situations appears a central extension of this algebra.
And what does it mean that the central extension?
Because sorry?
Is it anomaly?
This is due to the fact that if I
no H bar, but I guess that
it appears in some situations a kind of anomaly, especially when you consider the theory on a curved background. This is a coefficient, I mean, and then some correlators are proportional to this, for instance, scalar curvature, and this is a proportionality constant. But this is called a central term because there is, I never write this unit element. So in fact, I have to extend my algebra of modes by a unit element. Unit element commutes with everything, so it means it's central, and that's why it's called a central extension. Because we need one.
Okay, correct me if I'm wrong, but I believe that you can actually present it in a slightly different way. I mean,
this one?
The Witt algebra allows for the central extension, and then you say that given your particular quantum field theory, you pick a particular central extension with this particular central charge, right?
This may be so, but this is for me somehow the matter of terminology.
Yeah.
I may call this algebra with a central extension, and this is not my invention, a Witt algebra, and the extended version, a Virasoro algebra, right? But yeah, I mean, it's clear that this algebra allows a central extension because this is a central extension of the Witt algebra.
Exactly.
Yeah.
Okay, but usually when we quantize, then we may naively think that the commutation should be, I mean, commutation relations should be unchanged. So if there is some new term, then we consider this anomaly.
Sometimes it's called a conformal anomaly, but I mean...
does it break the rules of quantization, or it doesn't?
I mean, I don't know if I can answer a question which is answered like that. I try to construct, to find the representatives of these operators on my Hilbert space, right? And due to the fact that in the field theory, this Hilbert space is infinite dimensional, I have to make this or that way of normal ordering. These are terms which appears due to the normal ordering. So they are, in this sense, they are anomaly. Whether they spoil something, well, we give a consistent quantization procedure using this algebra of central extensions, so I don't know if it spoils anything. Maybe I don't know to understand. I don't prevail.
Is it Lie algebra or not?
Oh yes, this is a Lie algebra. Centrally extended Lie algebra, but Lie algebras allow central extension. You have a Lie bracket, right, which is expressed to, I mean, you can formally add this unit element 1 to the algebra. You do it, right? And then you have a bracket or two elements of algebra given by the elements of the algebra themselves. So this is a Lie algebra. This is an extended Lie algebra being itself a Lie algebra. Okay, now I want to just show very briefly the structure we have then in quantum conformal field theories. This theory, then, because it is to be conformal, so somehow by definition, this Hilbert space of the theory needs to carry a representation of the Lie of the Virasoro algebra. And in all such conformal theories, Hilbert space can be decomposed onto representations of the Lie algebra. Okay? This is somehow almost a defining structure. Well, they don't have to be, maybe different representations, but typically you use the so-called highest weight representation. And you can think of them as just a natural generalization of the representation of the Hilbert space of the harmonic oscillator, right? You have a vacuum, which is a highest weight state, annihilated by annihilation operator, and you act with creation operators. Here you do the same. You have a ground state, annihilated by all positive modes, being an eigenstate of L0, which is related to the operator of translations, scaling transformations, and then you act with all possible creation operators. This forms a representation space of my Lie algebra. Since I gave you the rules of commuting of L's with themselves, it means I know how L acts here, and I have a representation space. This is the possible way.
What is
Sorry?
What is new?
This is this highest weight vector, right? It's defined by being annihilated by all else and being an eigenstate of L0. Okay. This is a representation space of my Lie algebra, and this is some or in some models it's a sum, in some models it's a direct integral, depending on the model. But this structure is present always. Okay, now we have something which I'm not going to explain. Detail state operator map. In the CFT, once you have a state, you have a local operator. Once you have a local operator, you have a state. Map in this direction is straightforward. I take my unique, by assumption, ground state with scaling dimension 0. This is true vacuum. And acting with an operator with an index alpha, I'm taking the arguments to 0. I recover this highest weight state with addition with other value of L0. So I wanted to somehow highlight two things. First, we have this decomposition. We always know how the Virasoro algebra acts, and we have state operator maps in the theory. Next, those operators commute in a specific way with generators of the Lie algebra. It's not necessary. We have a.
So what is the role of this function B?
This is a.
When Z is not.
You can decompose it onto the maps between different spaces like those. This kind of a sum of interpolating operators. Right? And those interpolating operators are uniquely determined by the theory, and their coefficient constants in the decomposition of V onto these interpolating operators are structure constants of the theory. I need them to, well, I can answer questions about them to some detail, but as I told you, I try to be not to go too deep. I just need some notions. Okay, and I would be very happy to answer how to construct them. I would be very happy to say that whatever we are interested in conformal field theory can be obtained from the correlation functions of those operators. Okay, so this is they contain a basic information about the theory. Okay, a scalar product is defined by assuming a hermiticity properties of L's. Okay, so Ln Hermitian conjugated is L minus n, and this allows to compute essentially everything. A point of importance, interest, is the 3-point structure constant, which can be obtained by acting with V, 1 alpha on mu, and computing the product, the third one. So essentially, this is the structure of conformal field theory. Okay? Decomposition of Hilbert space, the possible values of alpha gives a spectrum. We have ISW vectors. We have 3-point structure constants and the symmetry. Okay? And then I would like to say something about the specific conformal field theory, which is a natural quantization of conformal factor of two-dimensional metric. Right? Once I have a metric on the surface, I have a invariance with any change of coordinates, which actually leaves me one degree of freedom, which is a scale factor of a metric. And then this is an action for the scale factor. I mean, in 2 dimensions, you cannot take Hilbert-Einstein action. It wouldn't make sense because it's just a total derivative. So if I have a Hilbert-Einstein action, I would just obtain a genus of my surface, which is a number, which can be used as a kind of measuring the strength of interaction, but doesn't give any dynamical information. So people will construct this type of action. As I said, phi may be considered as a conformal factor of a metric, its derivative, coupling with some background metric that we have. So for instance, you can see that phi is sensible to the singularities of the background metric, and an exponential factor, which is...
Why this form?
Sorry?
Why this form of action?
Why this form of?
Why the form of the action is just this linear in phi?
I can
exponential.
This action is, first of all, conformal invariant. Right, so I want such an action classically. I can show this, and in some sense, it's simplest. And in third sense, I can understand all the terms in the action quite natural. This is a kinetic term, right? Most trivial one. This is a cosmological term, and this is a coupling to the underground metric, which somehow shows that phi feels singularities of this metric. And moreover, this action appeared naturally when people, namely Polyakov, were studying the conformal, the string theory outside critical dimensions. And then he obtained this kind of action. But I'd rather not to go into that story. Okay, how Polyakov got this action. This action is nice. And essentially everything is known about it. We know the spectrum, which turns out to be just half positive real numbers. We know this 3-point structure constants that I mentioned for the theory expressed in terms of nice functions, gamma, Barnes functions, things like this. And the one more object which I need for this 4D, 2D correspondence is called the conformal block. And again, in this language, what I do, I take my operator V, which we have already seen, I act on this with some ground state, then I project the result of this onto the subspace with spanned by nu S, and compute the scalar product with this type of object. It contains, in fact, 5 indices. Written this way, this alpha is called an intermediate scaling weight and depends on Z here. It also depends on the central charge of the algebra, but it's there. Okay, so, and it's efficiently computable in many ways. Great. So, yes, sir.
So what is the role of this conformal block?
Because
I don't want to say what is the definition because
no. This is kind of description. If I want to compute in a quantum theory, well, I would say the theory is solved when I know all the correlation functions. Okay, this is kind of a definition I may adopt. And then if I have spectrum, 3-point correlation functions, and blocks, I can compute any correlation functions. So I needed to be able to write and compute all the correlation functions I may be interested in. But the second point, why I did not mention this on my previous transparency, is that the conformal block is not independent from the previous data. It can be computed just on the symmetry and the spectrum. Okay? So I needed to compute correlation functions to solve my theory. Okay? And as I said in this on the slide, in this specific theory, everything is known. Not analytical. And this function is complicated. You cannot write down in a closed form, but all you want to know about it, you know. Okay? Great. So this is one side of my correspondence. You may remember I'm going to talk about the correspondence between 2D and 4D. This is 2D, the simplest case. Okay? Can I move to 4D? Okay, this is for you. Okay, and then everybody of us definitely heard about the gauge theories. We are physicists. And then we have a very specific gauge theory. To start with, the gauge group is SU2. Very simple. Then we consider some building blocks, okay? You may have, for instance, fields with 3 indices, each transforming in the fundamental representation of the group, right? So I have 2 by 2 matrices of this with the indices, say, A, B, and I'm multiplying. I think this is more or less clear how this matrices of SU2 in the fundamental representation acts on such object. So this is a field, and this is somehow a geometry behind it. Sphere with 3 holes, 3 points with this indices attached. And as we will see a couple of transparencies later, this is in some sense a pair of pens. Okay? And the second part of the structure is the vector multiplet, okay? Which has some complexified coupling. Once we have a theories, supersymmetric theories, we have in disposal just the ordinary coupling and the so-called theta parameter, why one packs them into this tau parameter. So this is on the 4-dimensional side. Matter fields and gauge fields. Okay? And this is a theory where one has enough supersymmetry. Okay, and I have some 2 pictures how one can construct such a theory. They are related to the quiver diagrams. I have some matter fields here, and they are coupled by the gauge fields in this or that way. One can explicitly write down a theory corresponding to such a graph, okay? And then there is one nice thing, which is maybe of technical, but those parameters appear. I'm considering such a theory not really on the plane, but okay, on the plane in some rotating system. And I need this rotating system because, well, if you are in a system which rotates, then any excitation which extends far beyond the rotation center becomes more and more energetic, right? Because it feels the speed of rotation. So this is needed so that all the configurations I'm considering, or in fact the Krasov was considering, are concentrated around the vicinity of the system, where this rotation speed does not make them too heavy. Okay? So you have like this. This tau is the coupling constant, and there are some expectation values of scalar field gauge multiplates, some parameters like masses, and then one can compute partition functions of such a theory. Via path integral can be defined. And since the theory is supersymmetric, in such theories we have 3 types of contributions: the classical from the action, 1 loop, determinant of kinetic operator essentially, and an instanton contribution. This parameter k is somehow counts the number of instantons, and you may or may not remember instantons are simple solutions. They are self-dual or anti-self-dual solutions of the equations of motion. Typically in Yang-Mills theories, equations of motion are 2nd order, but for the dual or anti-self-dual configuration, they reduce to the 1st order equations and can be computed. Okay, and then there is one. I have 2 slides, which I like very much, but I will probably lose most of you, so I only flash them because there is a very nice procedure. It's called equivariant localizations. Okay, you know, it's sometimes useful when you have in theory an operator like exterior derivative, which is important. You can form nice structures like cohomology groups. This can be generalized, and I'm sorry, I will not go to these details, but the point is there is a very natural situation where having some kind of integral, right? This is an integral with parameter t over the complex, over the space which contains both bosonic and fermionic variables. In quite general situation, it may happen that this integral does not depend, in fact, on this parameter t. So you can compute it in the limit of very large t, and then you see that only saddle point of this integral contributes. Okay. So I prepared this in my slides, but I don't think I need to go through this. The fact is that this entire integral becomes turns out to be T independent and computed only at through some properties of a vector field at the critical point. Okay, and then the same thing. I mean, I think you may believe me. If we have 5 minutes of time, we can go exactly through these 2 transparencies, see all the details, and you will see in an example how this equivariant localization works. So this is something simple in a sense. If you can give all the details on 2 transparencies, this is simple. Okay, and then this machinery, this is related to something which is called Dijksterman-Hackman theorem, localization theorem. You can use it in more complicated situations. For instance, you can describe all possible instantons that you have in series with SU2 gauge just by formulating some conditions on matrices. K by K, K by 2, 2 by K. And you can then parameterize all possible instantons with these matrices. There is then this procedure of using the equivariant localization, and you can compute contributions to the partition functions, contributions to the path integral from the instanton contributions. And then all these contributions are labeled by a pair of Young diagrams, which we'll see in a second. Great. And then the relation I told you about. This will in fact repeat 3 times, so I be the modulus of x. We have the parameters B, which is, you may or may not remember, is a coupling constant of my Liouville theory. How strong is interacting? And then there is a central charge, let it be. The parameters epsilon1, epsilon2, those speeds of rotations of my reference frame are related to the central charge. Then you have these parameters alpha in the conformal theory. They're related to masses and of the supersymmetric theories in 4 dimensions. We have expectation values in this gauge multipliers. They are related to this intermediate dimension alpha S that we have seen in the blog. And finally, since my Riemann surfaces can be sewn from this pair of pens like that, there are parameters of this sewing. I can take length of this curve, and I can take a rotation angle, and this in fact describes me how I can sew this pair of pens with each other, making a more complicated surfaces. So there is a precise dictionary between parameters of the 4-dimensional theory and parameters of the 2-dimensional theories. Okay, and then this AGT relation, which as you've seen was already published 14 years ago. This is a claim that first of all, this instanton contribution to the 4-dimensional partition functions is exactly equal to the Liouville conformal block, and the full partition functions is a correlation function. Okay, so I have a relation between theories in different space-time dimensions. Okay, and then there was a proof, mathematical proof, soon afterwards, that how to construct this relation to creating some special basis in my conformal field. This is also a nice result because this basis, I just show quickly examples of 2 vectors of such a basis. This is a basis which diagonalize infinite set of operators, integrals of motion. So in fact, it shows also that the theory, the conformal theory, is integrable. Okay, and let me give you an example. As I told you, I always want to have some example to see, and this algebra will be also needed. Else, for my Villas-Law algebra, we have seen them before, and this is an algebra which is called a free boson algebra. Just take for this is like a creation annihilation relation, just with slightly different normalization here. And another thing is that the operators positive and acts like annihilation and negative and like creation operators. And I can construct states of some basis of a specific base. Okay, this is something which is known. And in this basis, you can prove this AGT correspondence for, say, R4 space on one hand side and Liouville theory on the other side.
Yes, and the definition. So this Hilbert space is spanned by by those
On the Hilbert,
operators.
sorry, how can I get rid of this imposter? Because
So A with index M and N, they seem to be operators. For
absolutely, absolutely, and
Okay. Okay, and you take the Hilberts, you have the take the vector space or span by one, by identity, and by all those AIs.
this is in fact one particular subspace of my Hilbert space, the one which is a representation space of this algebra.
Is it obvious what is the scalar product in this stage?
I mean, the scalar product, I don't want to really go back, but this is defined by the hermeticity property in a unique way. That else hermitially conjugated, just change the index from -1 to +1 and so on. This is defined this way. And in the free boson algebra, I mean, this is again defined by saying that AM daggered is A minus M. So this is exactly like for the harmonic oscillator. This is the same algebra essentially, but comes in many copies. So you define in the same way as you do for the scalar product. Well, if I assume that I have my hermeticity properties of the operators fixed, then it gives me the scalar product. And I can compute this, one can compute the scalar products of those operators, okay, assuming that P themselves are normalized to 1. So this structure everything is fixed. Okay. And in general, okay, and I told you this about this example of integral of motion, they are also not. Okay. Yes, this was somehow the first step, the simplest AGT relation.
So what was the result of this? For example, this is
the result was, I mean, this. Let me go back to what is the result? This is the result. This AGT relation is what's there. Huh? We have a very specific relation. We can compute something in 4 dimensions, 2 dimensions, and some quantities precisely mapped there. Okay? And the next 2 slides were a kind of how this is proved that such a relation exists. Yes, I told you my point is to discuss this relation between 2-dimensional theories, 4-dimensional theories, and relations between 2-dimensional theories. This is what I'm talking about. Okay. Okay.
So what is the origin of this relation?
Sorry?
What is the origin of this relation? This observation is.
I mean,
do you understand this and how by different means?
Oh, sure. I mean, you have the understanding in string theory, but I don't want to go into that. You start from the 6-dimensional theory, you consider some branes, and you can rub them in different ways. But I mean, so this was the motivation, I think, for the relation. But I really don't want to express it like that. So it's motivated by considering a single 6-dimensional theory on a product space, 2- and 4-dimensional, and then considering different ways of arranging some objects in those 2 spaces. So it's kind of.
You can prove it.
Sorry?
Then you can prove this.
You can, but the proof, I mean, this is the proof, in fact. The proof is purely algebraic. And it's, I always think this kind of brain constructions in string theory are kind of motivations.
Motivation.
But the proof is purely, I mean, algebraic, I would say. No. Okay, this is the claim. Right, so these examples. Okay, but then let me move to something, the other side. I mean, because I told you that the second, or maybe even the first point of my talk was a relation between 2-dimensional conformal field theories. Okay, and I will try to relate the 2. Okay? And this is some equivalence in 2-dimensional conformal field theories, which then I can use in this AGT relation. Was used. Okay, let me be a little bit more specific about this. I have told you what is the action of Liouville theory, so we can go back if I want to. This is now. Now, I want to tell you just a bit what is this supersymmetric Liouville theory, okay? So, I mean, the logic is this following. We start from the simple model, and then we try to understand more complicated model, more general models, this moduli space of the conformal field series, okay? I mean, this is a relation that was finally proven in 2014, okay, in the paper.
And there's a relationship between C and CL and CR.
Sorry?
There's a relationship between C, CL, and CR.
The relation between, I'm sorry?
Okay.
The upper line is related to the lower line.
Okay.
And
Now there's like some tolerant
I mean, this is a precise dictionary between correlation functions.
Okay.
Okay, and you'll see a bit more. And I mean,
Sure.
you can take one. You can represent highs with states of one in the vector space of the other. I will say a few words about it. Okay.
The relation in the is a relation you start from. Okay, so you said AGT start from 6 and supersymmetric period.
AGT stands for
Equivalences to Liouville or super Liouville.
equivalences. Now, the equivalence I'm speaking about is somehow horizontal. Let's say the AGT is going from 4 to 2, and now I'm equivalence on the level of two-dimensional theories. This is something else, but will be related to AGT. Okay, I'm building this kind of structure. Okay, I have an up-down relation. Now I'm trying to see some relations down there and use them with this relation to the up. This is four-dimensional space. Okay. And towards the end, I think I'll be able to tell you what is not known, okay? Because this is still something now in 10-year-old story, okay? Like that. So, and to see such relations between conformal theories, I decided to give the simplest, I think, possible example. This is not exactly the time I'll be talking about, but this is something that probably all of you have not heard about. So-called bosonization of fermionic algebra also. In 2 dimensions, there are so many symmetries that even you can express fields having one statistic through fields having another statistic. And this is the simplest possible situations. I'm taking my Heisenberg algebra, I have seen it before, right? I'm constructing kind of generating function. It's called a scalar field in this way. And I'm taking an exponential of this function. Normal ordered, creation, annihilation, normal ordering, perfectly well defined. But then you can expand it into modes, again powers of z, and you can compute that even if the modes of A commute, the modes of psi anti-commute. Okay? So in 2 dimensions, we do have different kind of relations, purely computational. And for instance, you can then define 2 natural operators in the spaces. First one counts, say, the sum of those lower modes, let's say energy. The second one counts how many excitations you have. You can compute a trace of Q to the 1, T to the N, the second, over the representation space. You can do it in fermionic space, you can do it in bosonic space, and you obtain Jacobi product identity. Okay? And in fact, it's sometimes said that this construction, the bosonization, mathematicians like to say, is a categorification of the Jacobi triple product identity. I mean, because here you have identity between numbers, and there you have a relation between dimensions of vector spaces. So this is certainly an interesting idea. Okay. And the bosonization is, I would say, the simplest example of relations between different conformal field theories. I think some of you may have heard about it. Great. And now let's go back to this relation. Right? I want to speak about. Okay. This term was already present for the Liouville. Now I have kinetic terms for my fermions. I have an interaction term, which after, say, integrating our fermions would give me the previous ones. I can construct 2 objects, T and G. I'm taking my bosons, they are no longer free. There is an interaction term, but it turns out that this object is purely holomorphic, does not depend on z-bar coordinates on my plane. This object is holomorphic, and they satisfy some superalgebra, this time called a Navier-Schwartz superalgebra. Okay? So I have, and let me stress quickly this point once again. I told you the theory is described by the symmetry algebra. I have just Virasoro algebra. At some point, I have Virasoro and free Heisenberg. Now I have Virasoro extended by these anti-commuting operators. This theory is also solved. And then once you add, I go down, once you add to these generators L and G one more object, free fermion, then you can construct on this space where L and G and free fermion acts, two copies of the Virasoro algebra generators. This is purely algebraic. One can check it, okay? And then one can show there is such a decomposition. Representation space of this algebra can be written as a direct sum of representation space of two Liouville algebras. This is an algebraic relation. The most difficult part in the proof of this relation is actually I need to construct highest weight states of these operators, well, in the representation space of those. This is quite an elaborate and construction, but it can be done, okay? And having this, we can actually prove the equivalence of those two theories. And then how this can be used? Okay, this can be used to demonstrate that we have more complicated AGT relation. Now we have SU2 not on R4, but on the kind of orbifold where I assume invariance with respect to some reflection, okay? And this turns out to be equivalent to the supersymmetric Liouville theory, and the proof uses this Liouville, double Liouville correspondence, right? I know what is for Liouville, so now I have a theory which has two Liouville theories. I can relate those two, okay? You have then more complicated space. Now this can be, absolutely.
So you say you proved this super Liouville.
I didn't, yeah, we proved this super Liouville double Liouville together.
Was it proved earlier, before this work, or after this?
Yeah, the proof of the equivalence was after this work, I mean, almost simultaneously. But the point is that they had arguments for this relation. They checked it in some spaces, and we have proven it as something which is a mathematical fact. But those gentlemen, well, they knew very well that it holds, just didn't perhaps bother to spend enough time to prove it correctly. Okay? Great. Now, some generalizations, because we have so far theory on R4 mod by Z2. Well, we can have this AGT correspondence also if we have more complicated spaces, more complicated orbifolds, and this is related to so-called parafermionic CFTs. Great. Of course, we had SU2. Now we can replace it by SUN group, and this is also known what corresponds to on the conformal field side, and other Lie groups, even exceptionals, this is also known. So quite a lot is known. And let me now proceed to the last part of the talk, because there can be more structure in conformal field theory that we have seen so far. And this more structure is called affine symmetry. And this will be the last, somehow, point of my talk. Okay? What is affine symmetry? Now, we may consider the so-called West-Zumino-Novigo-Vital models, which are maps from space to some group manifold. And taking the simplest action with the addition of the so-called some additional term, you can construct fields which depend solely on Z holomorphic fields. You can have their components, and those components satisfy this type of algebra. And you can see this is again a central extension of a Lie algebra. And so we have similar spirits, but this time the coefficients, there are constant terms and no m minus j. So this is a different type of algebras. And then one more thing I wanted to show you, because if you ever deal with the CFT literature, then most likely you would stumble upon the notion of the operator product expansion. So this is just a different way of expressing commutation relations between modes. Here, I think everybody knows what it means, a Lie algebra with some central extension. Here, the relation written in such a way means that once I take such a generating function in the correlation function, then the correlation functions of the right-hand side is equal to the correlation function on the right-hand side up to terms which are regular for Z going to W. And it actually allows to compute, to relate the different correlation functions. It actually leads to the standard word identities in such situations, okay? What is important in this type of models? Well, you can construct, having two such J fields, an object T, and if you want a detail, we can interpret every term which appears here as being related either to central extension of the algebra or properties of the group. And then from this definition, you can show some OPE. I told you this is a relation which is supposed to hold in correlation functions. And you can rewrite these identities in terms of this algebra, okay? So now we again have a conformal algebra here, if you have sort of algebra, with some additional structure, additional, more interesting structure. And then you do essentially the same, okay? You can construct a representation space of this algebra as before. We have some highest weight state annihilated by all operators positive modes. We have a Cartan subalgebra of this algebra, and all those vectors are eigenstates of this Cartan subalgebra, and then we act with rising modes on the states. In this way, you construct, again, the highest weight representation space. And I know I'm repeating myself, but this is something I'd like to pass. In all these constructions, we typically use highest weight representation spaces, okay? And then we have proven quite recently, together with my previous PhD student, that there is an equivalence also for this type of theories. This work is still under review in Communications, Mathematical Physics, not yet published. But I mean, it's solid. So now we relate two types of theories. We take this affine theory I have shown, I have blinked a second ago, for some levels k and 1. And then we show that this is equivalent to a theory where a symmetry is the direct sum of, again, SL2 and the Virasoro algebra. And again, you can mathematically prove it. There is a huge, in fact, machinery to show this. Some results we obtain, I did not go into any details of work. For instance, some of results, we have some identity between characters of different subspaces, which is a kind of generalization of this bosonization formula. And as my next to the last slide, I want again to relate it to something in 6 dimensions. You may remember, for now, in this 4-dimensional theories, we might have different gauge groups, we might have different spacetimes with these quotients, and now it turns out that you can also add some so-called surface operators or defects. And to be precise, in my 4-dimensional gauge theory, I have gauge fields, and the defect, I mean, is just some discontinuity in the gauge potential. This is a defect. So I have gauge potential satisfying some additional conditions. I can compute my instantons and so on. And the results that we have, this one I blinked a second ago, means that we have a relation between instanton partition functions for this group, but for different gauge groups. This may be interesting. This may be interesting to see a relation between computations 4-dimensionals, especially instanton partition functions for different gauge groups. Okay, and then there is a very natural thing, the last thing I want to say. You see, here I wrote that one can interpret this as corresponding to the gauge group SUK. But in the algebraic construction, this K is a complex parameter. That would be nice to understand if we have something like AGT for the non-integer, maybe complex values of K. Algebraically is okay. Geometrically, I don't know if it makes any sense, but we have all the necessary formulae. And I believe this is a good point to stop. Thank you.
We have time for comments and questions.
I told all the suffering goes to Rada doskonalości naukowej. So,
Can you explain why four-dimensional theory is explained by Riemann surfaces?
sorry, I have to.
And can you explain why four-dimensional theory is explained by Riemann surface function?
This is kind of, where do you parameterize it, okay? I need to go back very, very far, okay? To these pictures, I'm sorry for this, but I'm afraid it will still take 10 seconds. Okay, you see, on the right-hand side, I have quantities in four-dimensional gauge theory. Some field with three indices, okay? Three fundamental. So this field is something that contains three labels. And I can think of these labels attached to the 3 points, say, on a sphere, okay? I have a gauge multiplet, which transforms in the adjoint representations. So I can attach such a sphere to such a tube on both sides, okay? Everywhere where I have a dot, I have an index here. And this index can be contracted with something like this. And why I have a tube between two such a beasts? Because the interaction between matter multiplets, this is mediated by gauge multiplet. Okay? This is how you couple matter fields. You insert between them a gauge field, mediating the interaction. And that's why for every such a situation, right, I have some field here, my index, one of the three indices, is connected via a gauge field to another matter field. Here is more complicated interaction, but all this can be viewed as here I have sphere 1, 2, and third puncture connected via this tube to another sphere with 1, 2, 3 punctures, this one again connected. You can make more complicated graphs. Between two matter fields, well, you can have, I don't know, it may be hard to imagine how to construct a matter field which has two gauge boson mediating between two. So I'm not sure if in this way you can obtain a general quiver graph, but at least I think there is an easy way to see how this is related to a punctured Riemann surface. Okay, wherever you have this round object, this is a tube connecting spheres, and wherever you have the square object, this is an external puncture, where you have some matter field.
And the labels are just labeling different fields, like A, B.
Those labels?
Yes.
Here, the label means just the fundamental label of SU2. So for SU2, it just takes two values, 1, 2, right? This is the label, the element, matrix element. But you can have more complicated groups, and then depending on the representation of a group, you may have different labels, right? Fundamental representation, SUN, you have n labels. Adjoint, n squared minus 1, so on. So this is this somehow the picture between composition of matter and gauge fields and the Riemann surface. And I don't want to explain how it comes from the string theory and compactifying six-dimensional theory. Because
Could you understand this in terms of Feynman diagrams somehow?
this would be trivial in a sense, because I have enough supersymmetry, so my Feynman diagrams have no loops. In perturbation theory, I have only classical contribution, right? I have my first correction, determinant, I mean, this type of contribution, then no higher corrections, so no trivial Feynman diagrams, and then instantons. And I don't think if you can write contribution from instantons using graphs. So, I mean, this is, in that sense, is trivial.
Proper Feynman diagrams, but idea is kind of analogous. It can be partition function for this whole theory, but
that's exactly my point.
But they are not as Feynman.
They are not.
It's instanton contributions in a sense.
You mean this is not representative contribution?
Instanton? No, it's not. No.
Okay, so this cannot be expressed in terms of Feynman diagrams because this describes the non-contributive contribution.
This is what idea is similar. We build partition function for the whole theory from kind of elementary building blocks by.
But they correspond to a kind of Feynman diagrams, I would say, in string theory, where the propagators are surfaces and not lines. But I don't know if this is. Sir.
I have some question for one of the last slides.
Sorry for this, a lot of
You
them.
mentioned that your results give some idea or how to find for this work on what you done.
Yeah, this is, I'm sorry, I need to go back. Yes, I mean, you see, here we relating at level k and k plus 1, and right, this is the relation. This theory, I mean, this theory, such a symmetry, is related to this theory.
Okay.
And they have different.
Question about this first though. This result is a step toward the proof of equivalence of certain CFT.
Yeah. I didn't tell you, now I just gave you the symmetry algebra, right? And I can construct models with this symmetry algebra.
What kind of models?
Vita and WZ and W models, or depending on whether K is greater or smaller or something, theories describing hyperbolic three-dimensional spaces. And so the models are known, and we know much more than just this algebraic relation. But for my talk, this is not important. Okay, this is just the symmetry algebra, and you can construct states of one in the representation space of another. But then you have to show that correlation functions matches. There's some nice relations between structure constants of WZ and W models. I didn't get into that.
Sometimes is that a relation I'm curious how two-dimensional supersymmetric matrix is again, because is there a relation between space-time supersymmetric space or not?
Not really, but when I say about supersymmetry in two-dimensional space, I mean that I have some generators satisfying the superalgebra, anticommutators, okay? There are some of them, those corresponding to the labels, the lowest one, -1/2, +1/2, which may be understood as a translation rotation operators on two-dimensional superspace. But this is more about it. In fact, this is just a part of a more general construction with parafermionic or even the coset spaces. I'm not going to discuss this. Much more, but sorry.
So let us thank our speaker.
Przepraszam bardzo.